All right, in lesson 8D, we're talking about trig ratios. This is where we really get into the heart of trigonometry, and you can go home and impress your parents by saying that you are now understanding trigonometry. You can see on the front page of our notes, we're trying to do a couple of things by the end of this lesson. You want to be able to define 3 trig ratios. There's really 6 altogether, and we'll talk about the other 3 later. But we're going to talk about 3 of those trig ratios. That really isn't, functions are something different. That's probably a misnomer. But the 3 ratios that we're going to be talking about are sine and cosine and tangent. And then we're going to be able to make use of those when looking at 2 different types of angles that we call angles of elevation or angles of depression. Okay, so the first thing that we really need to understand is what these ratios could possibly look like. And I had mentioned on the front page, the 3 that are listed are sine and cosine and tangent. And that's what this big red S and C and T stand for. Okay, so this S in here stands for sine. That is one of our trig ratios. This C stands for cosine. That's a second trig ratio. And T is just tangent. And remember, a ratio is just a comparison of 2 different values. So the values that we're using are side lengths within a right triangle. So let's take a look at sine to begin with. Okay, in a right triangle, and sine, cosine, tangent, all of this stuff having to do with trigonometry only works with right triangle. So let's first of all look at the sine ratio within a right triangle. If you look at the diagram up above, if we're going off of that angle up here, which has that kind of goofy looking egg-shaped circle with a line through it, that's called theta. That just means that's the angle that we're looking at. And if you take this angle and go across from it, opposite it, you're going to end up with this side. Okay, so that side is considered to be the opposite. The hypotenuse in a right triangle doesn't change. It's always going to be across from the right angle, so that has to be the hypotenuse. And then the other side that's close to that angle would be considered the adjacent. Now it's crossed off in the diagram because we're not using the adjacent side, because the sine ratio is made up of the opposite side compared to the hypotenuse. We don't really care about the adjacent in the sine ratio. It's opposite over hypotenuse. And it's a ratio where the opposite is the numerator and the hypotenuse is the denominator. Now we use kind of this acronym that helps us remember this. The acronym is SOH, S-O-H. The sine is the opposite over the hypotenuse. We can do the same thing when we look at the cosine. We call that CA, C-A-H, because the cosine compares the length that is the adjacent side as the numerator compared to the hypotenuse side as the denominator. So the cosine is the adjacent over the hypotenuse. And then finally, the tangent, which we remember with TOA, excuse me, the opposite side is the numerator, and it's the adjacent side that's in our denominator. Altogether, we can kind of think of this term SO, CA, TOA to remember those different trig ratios. So a trig ratio is a ratio of the lengths of any 2 sides in a right triangle. It has to be a right triangle, otherwise it will not work. You're going to use trig ratios to find the measures of a side or an acute angle in a right triangle. And down below you see this diagram that shows really 3 overlapping triangles, but each triangle has this 21-degree angle in the corner. Okay, so if I look at just this triangle, it's got that 21 degrees. If I look at a larger triangle, it's still got that 21 degrees. What I'm trying to show you here is that it doesn't really matter which one of those triangles we're looking at. If I wanted to say, let's find the sine of this 21-degree angle, I could choose any one of those three triangles to solve for, right? And if I'm looking for the sine, let's see, that would be SO katoa. Sine is the opposite side, which takes me all the way across. It'll be this side as my numerator, and I'm comparing that to my hypotenuse, which would be this side. Okay, I could take that, and that would be the sine of 21 degrees. That would be no different than if I decided to use a smaller, one of those smaller triangles. Let's do this one. And I decided to pick out the opposite side and compared it to the hypotenuse here. I would get the exact same ratio. The reason I'd get the exact same ratio is because all of those are similar triangles. So for example, triangle AED, which is the largest one here, that's the same as triangle AFC, AFC, which is the same as triangle AGB. Okay, they are all similar. In other words, the ratios that come from all those similar triangles are going to be exactly the same. So it doesn't matter which one I look at if I want to find the sine of 21 degrees. That ratio is going to be the same.